Well, hello, scholars. We're going to take a look at graphing rational functions. Got some easy steps for you to follow here, and a lot of the parts of the graph, the characteristics of the graph, you can certainly be able to see actually just by looking at the function itself algebraically. So, when we think about what a rational function is, you want to recall that a rational function is really just one polynomial divided by another polynomial. Remember, polynomials can have exponents that are whole numbers, so we can have linear or quadratic or cubic polynomials, and those can be different sizes. They can be, just monomials. They can be binomials, trinomials, things like that. We practice simplifying those. With that, the one thing to keep in mind, though, here is that these polynomials, the denominator can't be 0 because obviously that's undefined. So you can't have a polynomial divided by 0. That doesn't exist. So in order to have a rational function, we have to have these two. So the steps to do this, to graph it, is we're going to look for some characteristics and sort of set those up to find the boundaries and some different features, and then we'll be able to graph it. So the first thing we want to do is simplify the function. So we're going to try to factor any trinomials. Let's factor those down to binomials. If there's common factors, factor those out. It's just going to make it easier to work with. And step 2 is we're going to look for the x-intercepts by setting the numerator equal to 0. So the top of the top polynomial, if it's factored, we're going to look for things that make it equal to 0. That's going to tell us where it crosses the x-axis. And then the next step is one step we're familiar with, is that if we look for the denominator and figure out what makes that 0, obviously that's going to be a vertical asymptote for the graph. So we're going to be able to see that. Then taking a look at the horizontal asymptote, we've got a couple of different cases to look at. So the horizontal asymptote depends on what polynomials are in the numerator and denominator, and more specifically, what's their degree. Remember, the degree is the highest of the terms, highest exponent of all the terms in the polynomial. So, first degree are linear, second degree are quadratic, and so on. And if they're put in standard form, it's usually the first term. So when the higher degree of the two polynomials is in the numerator, actually there's no horizontal asymptote at all, and we'll see this in a few graphs with that. So that's one thing to keep in mind. If the higher degree is actually in the denominator, right, so this is the higher degree in the denominator, then that's similar to a reciprocal function where it's the x-axis, or y is equal to 0. And then if the two are equal, so if it's a linear over a linear, quadratic over a quadratic, the horizontal asymptote is actually the value of the two leading coefficients. So if you take the leading coefficient of the numerator, the leading coefficient of the denominator, that ratio, that value is that's the horizontal asymptote. Then there's one interesting thing about rational functions, and that is when we simplified, a lot of times we ended up with one pairs where we sort of canceled them out, we said, or eliminated them. And those factors actually are going to create what we call a hole in the function, because it ends up being a point of where it's undefined. So keep that in mind, that anytime you see a common factor, both top and bottom, when you're simplifying, that's actually going to be a place where you're going to want to note that there's actually a hole in the function. So we're going to just do like a big open circle there to do that. So we'll encounter that a little bit later, and we'll demonstrate how that works. So with this first example, we're going to go ahead and look for the characteristics. So we don't need to, step 1 is to simplify. It's already simplified as two factors, x minus 4 and x plus 1. There's no common factors there. So the first thing we want to do is look at the x-intercept. So remember, that's the numerator. we're going to figure out what makes the numerator 0. So you could do just a real simple equation like this and say x minus 4, when is that equal to 0? Clearly when x is equal to 4. And we want to look at the vertical asymptote next, and that's going to be when the denominator is equal to 0. So when is x plus 4 equal to 0? Clearly when x is equal to negative 4. So remember that the x-intercept is actually a point, and the vertical asymptote is actually an equation of a line. So if I put this equation here, and we'll put that point on there in just a moment. And then the horizontal asymptote, because these two degrees are the same, notice that we just look at the leading coefficients. Now the coefficients over there on the equation you can see is just 1 over 1. So that means that the horizontal asymptote is equal to y equals 1. So I'm just going to draw that over here. And then because nothing was common in both the top and the bottom, there's really no holes in here. And so then the domain and range are really just all the x values except for negative 4 and all the y values except for y equals 1. And if we graph this, and you could graph this on Desmos as well, just to get your kind of the sense of where this function is, this would be what that rational function looks like. And so the key characteristics we're going to look at, obviously we want to see the x-intercepts, the vertical asymptote, and any holes or the horizontal asymptote that we're using here. So here's another example, and we're going to start out by simplifying it. So you can see that the top is a difference of squares, so we're going to do x minus 1 and x plus 1, and then the bottom denominator is just a linear factor, which is x minus 1. And what you'll notice here right away is that we've got common factors here. And this is a 1 pair, and generally we'd eliminate that. But remember that this is actually going to then create a hole at this point. And if we plug that value into the function, for instance, we plug 1 into what's left, which is just x plus 1, we get y equals 2. And so that's why the hole is going to be at 1, 2 with that. Now you can see that this graph is actually, when we simplify it, is actually just a linear equation. X plus 1, slope of 1, goes through the y-intercept of positive 1, has an x-intercept of negative 1, 0. But it does not have a vertical or horizontal asymptote. Notice that the numerator degree is higher than the denominator, and so again, according to that case, we don't have any horizontal asymptote here. And then that hole, notice that I just sort of exaggerated the open circle at 1, 2 to emphasize that that's the case. Now, if you graph this on Desmos or your graphing calculator, you're going to have to zoom in a lot and actually just look specifically at that value. If you hover over that value at 1, it will show you the hole, but it won't show you unless you actually hover over it. So that's why it's important for us to recognize anytime we're simplifying, anytime we see those 1 pairs that we want to eliminate, that's going to be where a hole is for the graph. All right, so one last example here for graphing, or at least finding some characteristics of the rational function, and that is we've got, notice the numerator is just a linear term, x plus 5. The denominator, we can factor this, x plus 5 and x plus 4. So notice we've got a 1 pair, which means that we're going to have a hole at negative 5, and if we look at the function that's left over, notice that we'll have 1 over x plus 4. So if you put in negative 5 here, you'll end up with negative 1. And so we know that the hole is right there. Now, notice that the x-intercept, there's nothing in the numerator that could be 0. So there's actually no x-intercepts. This is going to cross the x-axis at all. And if we look at for a vertical asymptote, the denominator obviously x plus 4. If x is negative 4, clearly that could be when making the denominator 0. And the horizontal asymptote, because this is similar to our rational function or reciprocal function, and the value of the degree is higher in the denominator. So according to that case, our horizontal asymptote is equal to 0, y equals 0. And so if we graph this, notice that again, I'm just going to exaggerate where that hole is so that we can see that. And then in the domain, notice that we have to exclude actually two values for x. -4, given that that's the vertical asymptote, and then also -5 because that is where the hole is. So keep that in mind. And then the y value you also have to exclude out of all the y values. You can use all of them except for 0 and -1 for exactly the same reason.